I wish I had the money like what some of these bigger companies have. If I had the investors, man, the cool kick-ass all-band amplifiers we'd make that were type accepted. Whew, I swear. I mean, the guys at Tokyo High Power really think everything through. This is a piece of cardboard that is designed to pull this thing in and out of its stock packing. This isn't how I wanted this video to start, but this is where we got to start from. I shot the preamble to this already. Like, I've had this whole amplifier completely apart, and we've already figured out what's wrong with it. But I can't find that video footage. I don't know where it got off to, but this is the little guy. This is the 1.2, I think. And I got the big boy. It's come back. It's sitting over here too. I got another one anyhow. Let me store all this up. So I cannot stress this enough, y'all, that the Tokyo High Powers don't like being keyed out of band. So if you're on 80 and you jump to 40, you better make sure this thing's on 40. And the same thing with his bigger brother, the 2.5. Or the 2 point whatever it is. It's the 1.5, sorry. This one here has 4 blown final MOSFETs in it. There's nothing else wrong with it. But you guys remember from the previous one of these that I did, how big of a giant chore that is for us to change out those MOSFETs. Hey buddy. I just put my dog outside, and apparently he'd been outside long enough because my wife just brought him in and threw him out here. Hi. Say hi to everybody. Why? Where are you going? Where are you going? Let's go over here. Where are you going? Hi. Say hi to everybody in YouTube land. Hi. Okay. So anywho, make sure I got all the screws out of it. I love working on these things. The problem is trying to find the parts. I got a big old speaker over here, and I just set the lid down. We'll say here's the speaker over here. I set the lid down and went think. Sucked it clean across the workbench like 2 foot. Stay. Okay. The parts are so hard to find. It's ridiculous. But in this situation, with this particular amp, these transistors that are in here, it's like everything else on the internet now. It's completely flooded with ubiquitous bullshit transistors. You know, because in the Chinese market, oh, hey, we can sell this part. Well, we got this other part here that works kind of the same. Let's just put a label on it and sell it into the American market. Those dumb Americans don't know any different. Once again, no standard. Not happy. Not happy. Fine. Do it the old-fashioned way. Come on. So what we got to do is we got to rip this PA board out. And then we got to take the thing all the way down. And if you guys remember from the last one of these I did, we learned that it gets much easier to work on once we take the board off the pallet. The copper spreader that's in here, that is. So we'll get these out. Pull these 4 little screws out. We'll rotate this thing around. Very carefully pull out the PA section. So first thing we want to do is undo this BNC. we'll do the output, pull it out. And, oh yeah, how do we know the final section's popped? Well, we've had some fire, scorched earth, and released smoke. That's how we know. So, the miracle of this entire story is what's in this FedEx envelope. A friend of mine, a very good friend of mine, worked with a company to have his own components built. And when it was all said and done, one of the part numbers that they built for him was called the SC400. The SC400 is this exact same transistor that's in here, the SD2933. That same transistor is a relabeled component where they put his own part number on that transistor. So, now if you guys can remember the last one of these I worked on, my saving grace was that the customer had sent an extra set of transistors with that amplifier. Well, this is the opposite way around from that. I had to figure out where I could get parts for this amp. Otherwise, this thing's worthless. Well, my friend that has these parts, it took a couple months to be able to get him because of his other career that he has, which has nothing to do with this, the RF world. I had to wait for him to get home, and then I had to wait for his personal life to slow down, and then I basically had to beg and plead. I had to get down on one knee and then both knees, and I had to beg. But I would say, based off the solder work that's on some of these parts, that this thing has been apart once or twice. Like somebody has pulled the transistors out of here before. But what we got to do is I got to go dig out the 1.6 ohm or 1.8 ohm. I got to go look at the schematic again. There's a few of these resistors that get burned. I got to go dig those out of the part drawer. And then you and me, we're going to pull this whole thing off, and we'll pull the transistors off. So give me just a minute. Let me get the parts all lined out, and then we're going to take this all apart, and we're going to get these transistors pulled out and swapped. Let's see if we can get this camera to focus here. Look at this. This has been taken apart by somebody at some point or another. That's little spalls of lead. And the way this came off of the spreader is like this. So underneath this MOSFET sits on this spot on the board. And there's nothing in that. There's clearly two different types of thermal compound on that pocket. And it is all full of garbage. Okay. This transistor here is the one that's had its lid removed internally. And once again, we got a big mountain of solder flick right underneath the bottom of the transistor. So I'm not pointing any fingers, but whoever took this apart didn't do a very good job cleaning the pill pockets, nor did they really care, for whatever reason. So I'm sure I could call the owner and get the history, but it doesn't really matter. My job now is to remove these 4 transistors and do some board repair over here. So I'm going to do that, and I'm going to save you guys the heartache and the sorrow of watching me work. Give me just a second, we'll return. I think I'm ready to have you guys join me again. So cleaned all the old thermal compound off, and we did that because it was completely impregnated with, well, garbage, as we've seen from this one transistor here. I have a feeling that one of these is still a good transistor. I know for a fact that, well, that one's bad. Most likely that one's bad, and most likely that one's bad. This, what I think has happened is a classic, whoever's supposedly the technician doesn't really know what they're looking at. So these two were paired together, and these two paired together. Let me explain to you what I'm talking about. Let's get in here and let's look really closely at these components. They all share the same part number. These aren't the same manufacturing date, not the same lot number, nor are they the same reference number on any of them. Now, we would like to believe that they're all the same component. We would like to believe that we live in this fantasy land where if it's got this part number on it, that means it's interchangeable with this part. Like I said, we live in a land, in a world, and in a universe where that's not necessarily the case. We can see that these are supposedly all the same manufacturer, but then in the same breath that we can see that they're not the same components. At least not on the labeling font, the style of font, or the style of text. I would believe, based off of the last one of these I worked on, that this is the only legitimate component in the whole amplifier. Possibly this one as well. But primary thing that leads me to that conclusion is the cut tab legs, specifically these, and the print. I feel that these two are definitely eBay or Alibaba Chinesium copies of the component. But if my theory is correct, one transistor has blown, this amp went to somebody, then it got another transistor popped, and then they replaced another one, and then they eventually said they couldn't fix it. What we learned from the last one of these that we worked on together, you guys and I, is that these resistors here have a tendency to either pop completely with no resistance or they'll burn completely up. I had 1 out of 3 that was good. Specifically, this one here on the end was the only good one. This one here. That resistor sits between the gate power supply and the gate trimming circuits, which are here. If I remember correctly, I got to go look at the book, but don't quote me on this. This is rough, coarse, and fine. So rough voltage, coarse, and fine. Okay. Those resistors are the sacrificial lambs that sit between the gate of the transistor and like this one here is horribly disfigured. This is a violent collapse of the component structure, and it's represented here by how hard this resistor is burnt up. Well, this was the order to which they were in there. The only resistor that still reads within spec was for this one here. I just think it's odd. I just personally think it's odd that they don't have the same font, the same print, the same manufacture date. These have obviously been changed. So, I mean, we're gonna test these here on our Atlas. This is the DCA 75 Pro. Now, is it the most laboratory-specific device that has ever been made? No. Does it give us a rough, good ballpark figure on if the component is working or not? Yes, it sure does. So this is an N-channel MOSFET. .127 volts. is our gate voltage on this particular component. Full off, 1.212. Internal resistance is really low. Okay. So I was correct in my assumption that this part was good. I have a feeling that this one was bad based off of this resistor, but I could be wrong. So red and green, so gate and source are shorted. I'm not going to bother checking that one. This is the one I believe is stock. No component detected. So the gate, the source, and the drain are completely electronically separated from each other on the inside. So if we pop the top, it's going to look like this on the inside. If we pop the top, it's going to look like on this one. We pop the top on this one, it's going to look like this, but there's a mechanical short between these two legs. This one here, let's test this one and see how it adjusts. I know it's going to be wide open. No component detected. This is when the wafer itself is completely disintegrated, atomized into smoke, and there's no short. If we were to pop the lid on this one, we'd see that there's still a little internal structure left on the inside of the transistor, but these two leads are shorted together. So let's get our all matched components. These puppies are spendy. I mean, this is a really great component. It's not as good as like the 188 XRs and stuff, but that's a completely different class of device. And these parts predate those transistors by a lot. Still sensitive little devices, and they work great. 3.3. I remember that. 5 volt. Good. This thing is right next to going open, by the way. So let's see what our internal gate is on this device. .3. Let's run that test again. 3.3. There's our same voltage again. So that's good. This part is good. .34. Another strong part. Okay. Main thing I'm looking for is turn on max voltage. There we go. Sound on. 3.36. 5. So we're going to match these two together and these two together. Okay. Turn that old guy off, move it out of the way. I've never understood why people that work on this kind of stuff, it seems like they don't care. It's like they just want to slam the part in there and then slam the part out. This thing's got solder vias on it. Specifically here, 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 and here. if we flow too much solder on this side of the board, it'll pass through these vias and short out, and we don't want that. Specifically here, 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 and here is where we don't want to have the shorts. This isn't so important, as in it won't affect anything, but this here, this here, this here, and this here makes a big difference. So that's the reason we take this off. That, and I wanted to take my opportunity to do this right. I don't want to I need a pointy device. Here. Let's get down here and let's take a look at this. Let me explain to you what I had to do here. So, those resistors obviously come from the gate side of life, which is here, and they're isolated behind this capacitor, right? Well, gate side of life once again. Look at where that leg for the resistor sits. See that? See that? And then it comes out to this little tiny trace underneath the resistor here. Well, that translates to this little tiny trace on the bottom of the board, right here. Well, here's its parent partner, right here and right here. Well, to change that resistor out, this is a pass-through solder joint. So, of course, that means a little bit of solder, a little bit of wick, working it back and forth, and eventually the hole opens up. This here, this lead here, it's easy enough to remove the transistor or the resistor, but because it's directly underneath this surface mount component, it's really not the smartest thing to try and get this too overly hot, because then we can devaluate these capacitors. Or pardon me, these resistors that are here. I keep calling them capacitors, I'm sorry. These resistors that are present. So what I did with the other repair is that I brought the resistor across from the trace, the pass-through, here, and then I folded the leg back and soldered it in this area. And I'm going to do the same thing here, and the same thing back here underneath this resistor, and then I'm going to do the same thing here. I'll bring it from here, and then I'll solder it to here. So, makes the repair a little bit easier, but the main thing is we don't want to destroy those surface mount resistors. It'll cause too much time, too much energy, and I'm not going to go dig around and try and find those surface mount resistors if I don't need it. It's not going to affect how the amplifier runs. It's not going to affect any of the signal, but what we did do is we went through and we cleaned everything back to factory stock. So we have a nice clean work surface to go and solder to once we're ready to assemble this. What I did with it on the last go around was I mounted this back to the board loosely, set it down, then I squared up all my components for its points on the spreader and the heatsink, roughly soldered down the parts, and then removed the board again and did all the finished solder work. And that's probably what I'm going to do now. So I want to get this done. This thing has been sitting here forever. The customer that owns this thing has called me multiple times. And he wasn't rude about it. He said, "Oh, I'm calling to get an update." I got no update. I can't get any parts for you. Yeah, but they've got these, it's the same components are on eBay. They're fakes. He was having a really hard time understanding that there's such a huge market for knockoff transistors on eBay. Go buy a set of Toshibas off of eBay. Good luck with that. Go buy a 1969 final, or an MR477 final, or a 454, or 455. You might get lucky and find one that's a legit component, but 9 times out of 10 they're fake knockoff transistors from China. And I guarantee you that's what these are. These are fakes. That print looks legit to me. Look at that logo and that print versus that logo versus that logo. And literally, I mean, this is a color injection machine that shoots these logos on here. Who knows? I mean, the Chinese market, the more and more I look at the transistors that come out of China, forget it. Forget it. I mean, you want to see something scary. There's a YouTube channel says the guy's #1 video is called "I Built My Own Apple iPhone." And he lives in Shenzhen, China. Well, as he's running around trying to find all the parts, the aftermarket extra components that you can literally run around in China and build your own iPhone out of garbage that you buy from people in shops. I guarantee you, there's a guy out there that's found on market that he could sell probably these things for. He'll have them made for like $1 to $2, and then he'll upsell that to 30 or 40 American dollars. He's got one guy that does nothing but supply these, the capsule, the foot, and the ceramic base with the lids. Another guy that will cut the wafer for him, and that's their entire business, is making knockoff wafers. And so he'll make the wafer pattern himself. It's the same thing. Haigu HG does the same thing. They'll get the wafers made, and then he'll take them back to his little shop, and he'll assemble each one of these one at a time. He'll make 200 or 300, and then he'll take them down, and the guy that's got the machine that services the entire little district of shops that puts labels on shit says, "Hey man, put this part number with these other numbers on it." I got some HG transistors around here that just got the BBI logo on them, and the part number is 001. It was like an additional $5 to have my own logo put on the lid. But what's the point? We can't cross that transistor with anything. Nobody's going to know what that is if somebody is also trying to be a repair shop. This is a controlled known. You know what I mean? These were bought before the ubiquitous parts that were flooded into the market, and I know exactly what this is, and it's the exact same component. This part here and this part here were manufactured at the same time on the same product line by the same company. This just happens to have a different logo on it because my friend bought so many of them at that time that they put his own part number on it for him, which in my opinion is dope. Well, here we are 2.5 hours later. Ended up having to pull this resistor and this resistor. I got our 47 ohm resistors replaced. I replaced them with 47 ohm 1%ers versus the 47 ohm 5%, like what's called for over here. Let's go over here. If we look, we'll see right here, 47 ohm, 0.05 watt, 5%. So we have this temporarily put together and down, because now I got to stretch out my Jedi Knight soldering skills, and this has to be perfect. And once I'm done, I take it all apart again, and I check all the solder work on both sides because of those pass-through vias I was just talking about. So let me get this camera out of the way, and the last 4 or 5 hours of my life have been leading up to just doing these 16 solder joints. So let's get on with the show. Okay, this is all cleaned up and defluxed. 91% rubbing alcohol. Bottom side of this is perfect. I got no drips, nothing I'm concerned with. Nothing's hanging down too low. This all looks really good. This high spot, of course, is a capacitor. It looks great. So now, to put this on here permanently, then we go ahead and we'll set it into the amplifier. We'll hook everything up. We're going to pop out our 2 main fuses, and we're going to start setting our gate voltages. Okay, I hope this doesn't make you guys sick, but this is to save me a ton of screenshot and post edit. So explain to you what's happening here is this is our gate voltage here. It comes in, and this is our VR 205, which this is our coarse voltage adjustment here. Okay. So we're going to follow this trace down. This is VR2. This is our fine adjustment for this, this amplifier device Then here is VR203, which is our fine adjustment for this amplifier device. The line continues down, and we've got VR2 for this amplifier device, and so on. These are how I independently trim each one of the gate volts. Let's scroll over here to the amplifier real quick. This is our course adjustment, and let me flip the camera. Oh, don't quit on me now, display. I did. Okay. This is our, come on, boot up. Boot. Over here, these are our fine adjustments. This here and this here. Okay, so this is VR201, VR202, VR203, and VR204. So what we're having here is a problem that has taken place where I'm not getting any gate voltage to here. So we're looking at the gate here. So this is VR204, VR203, but we do have gate voltage down here. So we can automatically eliminate our coarse voltage adjustment circuit, our regulator, and all that garbage that's up here. And we know that this trace here that carries the Magic Pixies past these first two gate controls goes down to VR1 and VR2. Okay. Now let's come back over here to the amp. Let's make sure I got it in frame this time. Okay. What we have going on here is I have beautiful, wonderful gate control here. I've got my proper volts. I can dial them in where I want. Over here is 0. Remember, this is the one with the launch transistor in it, right? This is the one with the one good operating transistor-ish that's a knockoff. I have 0 gate volts here whatsoever. So then I start to back up the chain. So how it goes, according to the schematic, as our voltage comes in, and I believe this is a 2K variable voltage resistor, or variable resistor, then it passes through this diode here, and we're just going to break it down to this far end transistor because it's the exact same circuit 3 other times. Goes through this diode here as a protection, so there's no backflow possibility. Then it goes by this little capacitor that acts as a filter, and then we go through this 47 ohm resistor, and then boom, gets dropped right onto the transistor on a gate. A 47 ohm resistor is the sacrificial lamb. Let's come over here and look at it on the computer one more time. So let's look at that exact circuit, which is right here. And I'm doing this so you all explain or understand. I don't need this as a reference. I understand how this circuit works, but here's our variable resistor coupled to earth. Goes through our diode for backflow problems. Here's our filtering capacitor, and here's our 47 ohm resistor. Well, so then we start measuring back up the chain. So we're going to go look at the gate here, and there's this little tiny resistor here. It's okay, it's fine. And then we've got our 10K resistor that's coupled to ground. It also measures within spec. The transistor, as we've shown on video, measures within spec. Neither one of these capacitors that go to ground, which are the 2 little black capacitors that I identified as diodes earlier, these are 0.01s, 0.01s. That's also to help for isolation. My R216 to 47 ohm resistor, that's also in top shape. This capacitor reads within spec, and this diode reads within spec. So I have no gate voltage because I'm losing it between this feed line and probably from this variable resistor, because I have it down chain. So whatever is pulling the voltage to ground is present here, because this is a continuous circuit. And if I have it down chain, what I mean by down chain here is if I have it down the food chain of the circuit, because remember this is flows in a linear way, that our gate voltage comes in, goes through this trace, and it's tapped off to this resistor, tapped off to this resistor, continues on, taps off, taps off. If I've got power on this side of the circuit, I'm losing it right here. Okay, so now everybody's on the same page. Really what that represents is I got to do another check. I got to make sure that there is not an unreasonable short. So again, let me make sure I got all this in frame, because I'm kind of working opposite side that I'm used to working with here. Let's boost the gain up a little bit so you can read the voltmeter. We got it on simple ohm check. This side is going to be our control because it's working perfectly. So we're going to give it a ground source. And then we're going to read, we've got 10K worth of resistance here, which is perfect, because where we're getting that reading from is from the R219, R226, R224, R221 10K resistors. If we were to see significantly less resistance, anything lower than 10K, that would tell me that there's a fault in the device, as in far as there's a fault up chain. Remember, our gate control voltage flows from these devices up through this portion of the circuit and then to this tab on the transistor. So $10K. $10K. What I'm demonstrating with that simple resistance check is I'm not measuring the device, I'm measuring this resistor here. If the resistance was any lower than 10K, that would tell me that there would be something north, something on this side of the circuit that's pulling the electronic pixies down. So either these two variable resistors are not getting the input reference voltage that they need, hence meaning something upchain, which according to the schematic can only be a trace. Oh, calm down, Big Eye. This Fluke 97, I love it, but man, it's something upchain from these two. According to the schematic, it's going to come out of here, runs through, comes by, and then drops on a trace and feeds all four of these transistors. This is a new one to me. This is a new problem. So, unfortunately, all the good work that we just put in by having all the thermal compound and everything put in place to where it was all perfect, this board's got to come off yet again, and I've got to go figure out if it's really a singular trace that comes off of here, off of this trimmer pot, which we know works because I got good control over here, if the trace is broke down, or is it these two variables are chooched, if they're fried. Telling you, electronics fun. Says the clapping, dancing, smiling monkey over here. Fun. Yay. I'm telling you, it's a blast. This is interesting to me. So this is our trace right here. It's one continuous trace that goes to this trimmer, and then it goes to this trimmer. This trace goes by and it goes to these two circuits, which are working. So these are tied together, this whole thing, wide, please. This whole thing is tied together by one trace. So I've gone ahead and I've, here we'll look at this trace in reverse. We'll come down here and we'll grab here. Let's see, let's make sure I got the volt ohm meter in view here. So here is conductivity to this potentiometer, conductivity to this potentiometer, conductivity to this potentiometer, yes, conductivity to this potentiometer, yes, we've got that. All the way over here to where we pick up the gate voltage, so we've got good conductivity. So now we'll go and we'll meter these, and this, let me show you this first. I'm going to meter the output. So this particular transistor wants, because I was able to trim these into 2.5 volts, This particular meter wants 300 ohms of resistance. Or this particular transistor metered out to 300 ohms. This particular transistor wants 287.5. When I first probed these, they were in the 600 to 700 ohms worth of resistance. And the same thing going on here. So I went ahead and I just gave these a rough adjustment. As I go through my arc of movement, okay, let's reset this test up for you all. Just to show this to you on video. This is stuff I've already figured out. There's a good place to grab that trace here. Okay. As we go through the potentiometer's arc of movement, see how I can overclock it? So I reach a max zenith of 670 ohms, and then I can overclock it and it drops to 469, and that's where they were sitting, was in the 400 to 500 range. So I'm like, I went to twist these and I'm like, wait a minute, so bring them back around and we'll get ourselves down around 300 ohms on both of these. I don't see anything. Like, what's weird is I can go and here, I'll grab up this transistor, let's say. I can go a meter from the potentiometer forward. Well, we're passing through a diode in the direction that's correct. Okay. Passing through a diode, we've got the 10K resistor that's referenced to ground, and we're going through a 47 ohm resistor. There's nothing in the circuit that's dragging the voltage down to ground. I'm wondering if it was just the potentiometers are so far out of whack. But you'd think I'd have a little bit of reference voltage instead of 0.000. Let's put it back together and let's put power on it. Let's check it. Well, that's a relief. I mean, it's... Okay, so we got the Fluke 97 hooked up to the questionable bank, this stuff on this end. And then we've got the Fluke 73 hooked up to this bank down here. We're seeing roughly the same float voltage on DC leak, which is okay. I mean, it's nothing to get excited about. But now we've got 2.47 volts here, 2.47 here, and that's on our gate. And that's on this transistor, which was just shorted. And the same thing. Okay, so we were close. Just by tuning it with the resistance, we were pretty close. My question is, let me back this up a little bit, get a little bit more of this in frame for you all to enjoy. My question is, what happens when I go and I yard this sucker wide open? Let's watch. Okay. It was just way turned off. All right. I jumped to the worst conclusion I could possibly come. This is, all right. Easy enough. Let's de-energize the circuit. And, let me get everything screwed back down now again. Actually, I'm going to pull these 3 screws out. I'm going to lift the board up yet again. I'm going to clean off the bottom of the transistors with rubbing alcohol and reapply new thermal compound to the heatsink spreader. And the same thing with the input attenuator. I'll be back. Okay, I think we got all the screws set the way they need to be. And my train of thought was that the potentiometers that are on here were way out, like way out of whack. So let's go ahead, we'll turn this on. Seeing the same amount of float voltage here, which is fine. That's way below cutoff for the transistor. Way out of whack. So when I turned all the potentiometers to their maximum, and then I went and I took the course adjustment and adjusted it to 2.8. Now remember, our goal is to keep this below 2.7, because at 3 volts we know we have a problem, and I figure if I kept it at 2.8, the course adjustment, which is this potentiometer, then I could not have to rely so much on the fine course to get rid of, let's say, like a half a volt worth of current. Volts. So I adjusted up to 2.8 and brought the fine adjustment way down. I just started bringing it down. I'm going to bring it in at 2.5 volts. The last amplifier that I repaired like these, or like this, I sent it out of here with 2.69, 2.69. So almost 2.7 volts on the gate. We're going to start out at 2.5. The reason I'm going into this really slow is because at the time I thought these transistors were not all that expensive. Come to find out, everywhere's out of stock of them, and these are incredibly expensive parts. There's over $500 worth of parts that we just put in here, not to mention the insane amount of time it took me to get all this in here. So we're going to start out at 2.5. We're going to watch our current as we key it up for the first couple keys, plus we're going to watch the heat. Because I'm going to have 1 or 2 keys. If I have this set too high, there's going to be some serious problems. So remember, volts. So this is tenths, hundredths, and thousandths, right? So 2.99 or 2.2.499999. 2.5. 2.51 or 2.051. 2.503. 2.503.05. Just breathing on these trimmers will make them change. So 2.9998, 2.98, 2.5. These things are a little tricky, so we're going to go into this low and we're going to see what we get out of these components as low. Now, lower voltage, gate voltage, and we're talking tenths of volts. We're not talking volts. In the world of LDMOS, a world that I'm very, very, very comfortable playing in, a tenth of a volt makes a big deal. A tenth. So we're going to trim this up low and make sure that we're in the right mode of operation, and then we're going to see what we get out of the amplifier for power. And we're going to watch our current draw over volts, which will help us dictate the mode of operation that these MOSFETs, and these are MOSFETs, help us dictate which mode the MOSFET is in operation. So, all right, next step is to hook up the positive or the positive leads, hook up the coax connectors. Let's slide this up in here a little bit more, and let's put some schmoo to it. Let's get on with it. Over $500 worth of transistors. This is getting silly. Power supply volts, amps going to board, current gate voltage behind an isolated probe. We're at 2.6. We have 0 draw on the amp gauge, no voltage drop on the power supply, and transistors are not activating. And it's requiring a great deal of power to get these transistors to put any or let anything through. So that means we've already come up a tenth of a volt. Guess what, boys and girls? It means we pop the fuses and we dial her up another tenth of a volt and see if we can get the transistor to kick on. Okay, so now we're getting closer. So let's see, I put 2.7 in it now. And the fun bit about this is I don't have to adjust each one of these trimmers. I don't have to adjust each one of the trimmers individually. I just come over here and I grab the course adjustment and dial it up, and they all come up evenly. Kind of cool. Okay, so I got 52 volts here present on the power supply. We're putting 2.7 volts on the gate. We're starting to see a little bit of current draw, and now we're starting to see a little bit of power. So we've got a 0 through, or 2 through 30 megahertz, 50 watt element reading forward. And so we're putting about 5 watts into it, but step on the pedal, transistors are starting to turn on, and we're starting to see them heat up. So now, how we adjust this even further is now we're going to start to increase our gate voltage once again, 2.69. Go to 2.8. Still putting 5 watts in, and we're getting about 2 watts out, but we're seeing a load on the power supply now. We're starting to pull current at 1 amp. So let's just start creeping into it, and eventually it's going to kick on. I bet you it's going to be around 3 volts. Okay, so here we are at 2.95 at this point. Now we're starting to see some power. We're putting 5 in it, 4.5 out. So we're getting closer. Let's go ahead and we'll run this on up a little bit more. I was just on the phone with this nice gentleman. He wanted to get a 2-pill built. And I'm sitting there concentrating my balls off on this thing. And the phone rang, and I'm like, oh shit. Scared the underwear right off me. Okay, so now we're at 3 volts. 5 in, 4.5 coming out. And the transistors are all turning on with a little bit of input power, so we're getting closer. Still not enough current. So let's get on up there. 3.1. So now we've come up. There we go. Now we finally got amplification. What do I mean by that? Let's look at this here real quick. 5 watts going in. Whoop, a little bit more power than what we're putting in it coming out. So now this is where we start looking at these two figures. Two amps. All right. Let me get this dialed in. We'll be back. Okay. So where we ended up at is we started out at 2.5 and we slowly walked it up. Now what we're trying to see over here on the output meter is about 800 watts on my workbench with this radio driving it underneath full output. So we're going to see about, I mean, this is what we're working for here. Hello, 1, 2, about 80 watts going in. Hello, audio. And we want to see roughly a 10-to-1 power output. So maybe 70, 80 watts, 75 watts on 80 meters out of my ICOM 7300. And what we're looking for is a 10-to-1 amplification. Well, our gate voltage, we started out at 2.8 volt or 2.5 volts, and now we're sitting at 3.7. So we've come up 1.2 volts on our gate. And it hit this magic spot at 3.7. All of a sudden it went from and the current draw is completely negligible. So I don't want to run this for very long without us putting any air on it, but let's just watch the amp gauge on the power supply, knowing that we have 53 volts at idle or 52 volts at idle, and underneath load is dropping to 47. Hello, 1 2 1 2 1 2. Now, according to the paperwork, let me go back over to that PDF. If I can give it a little bit more, I'm going to give it, but I'm pretty happy with where we're at as far as output power. Let me scroll up here to the spec sheet for the power supply. Let's see here. Just want to make sure I say this right, because somebody out there is going to nitpick me to death. 20 amp, 10 amp. We're on 110 volts, so I guess I was looking at the wrong thing. AC line, DC voltage, DC amps. 35 amps max. 35 amps max. So we have to understand that this is an RMS reading clamp, right? Oh. Everything with this amplifier has been this way. So it's been a challenge. It's okay. You have these come through, and every once in a while you just kind of got to work through them and pull up your big boy undies. Hello, 1 2. So we're butting right up against that at 20 amps RMS. We're maxed out on power supply. But what we got going on over here is a beautiful thing. Let's look at this. It's a 1,000 watt element in peak envelope power. Here's the radio. Hello, 1 2 1 2. There's our 75 to 80 watts. Hello, 1 2 1 2 1 2. There's our 750-ish watts in output power. And that's where I'm going to leave it. I could turn the gate volts to 3.8 and maybe squeak another 50 or 100 watts out of it and leave it alone. The math is right. The current draw is right. The load on the power supply is right. Everything is right. Now, the other thing I'm not really thinking about is I do have this plugged into this outlet. I would bet money if I go and I get my 30 amp 110 committed outlet and I get it plugged in on the back of this thing, we're not going to have near the voltage drop that we're having come out of that one outlet. It's just my opinion. So now what I'm going to do is we're going to power this down, and then I got to wait for the electrolytic capacitor to completely discharge. And then I'm going to come in here, I'm going to pop the fuses up so this circuit's isolated, and then I'm going to remove these little test probes that I put in here so I could trim everything. But everything is within 1/100th of a volt of each other. I think I've created an environment to where these transistors are going to be relatively stable and safe. So, for the record, if you are able to acquire some SC400s for this particular device, I would probably be starting at about the 3.3 volt range and slowly working your way up from there on how to get these to turn on. But I'm going to pull the test points out, flip this over, put it inside of its cabinet, put the lid back on it, and we're going to hook it up to a committed 30 amp outlet that isn't probably at the very end of its amount. Do you think how much shit is coming through that outlet right now? I do believe it's the same circuit that's tied to the lights and stuff, so that's why I make it a common practice not to plug in there for a test. I'm just showing you that this thing is making the power that it should with the amount of current that's being drawn. So, all right, let's get on with it. Sometimes wonder about other technicians. So I went to put the lid on this, and I started thinking as I was putting the lid on, I'm like, the last couple of these I worked on had a 2-stage fan. The fan was always on, and then when it got really hot, it would go into high operation mode, which is indicated here on the front. I'm like, my fan isn't running on this amplifier. Why not? Well, this is our regulated DC to DC switch supply. It pulls the 50 volts that comes off the output primary filtering cap of the power supply. It pulls a little bit through this lead here, pulls a little DC off. This goes to a temp probe that works its way over here, and then this is our output. And I'm like, well, look at that. It's got a little 2 amp fuse. If any of you guys out there in YouTuber land know where I can get this weird custom made 2 amp, and the part number is LM-91. I haven't had a chance to do a YouTube search. If any of you guys will watch this, put the comment down in the doobly-doo, because I want to get a couple of them to have them sitting in a drawer, because I've got a couple more of these I got to go through. But I couldn't help but notice I didn't have a fan. And I'm like, no, the fan's always on, but then when it gets hot, it goes to high mode. So I don't know what the previous person did when they were in here, but they had their little dick beaters all over every gosh darn thing. They had the little dick beaters all over gosh darn everything, and like you can see, this is all scuffed up. There's a little spark mark over here. I don't know what those are from. It wasn't like that when it came here, but it was like that when it came here. I don't know what these are all from. But I can tell you that the guy didn't know what he was doing. So that power supply runs independently. It's a DC to DC switch mode supply. It's got an external sensor unit on it that engages different voltage settings for the fan. You have a low fan setting for normal operation, then you have a high fan setting for when it starts to see it get over 70 degrees Celsius internally. So it'll call for that second volt setting. But man, that shoosh. Man. If I would have gone on and tested this thing and let it get hot, and we would have blown them transistors out of here, I would have been so mad at myself. But we didn't. I caught it before it became a problem, so let's go ahead and unplug it. It pulls DC directly off this filter cap. So when you shut the amplifier off, that's one of the main things that presents a load to the electrolytic to pull it down. And without it engaged, it just sits there and it floats for a long time. So sitting there, I'm going, man, why isn't the DC bleeding off on this thing? And I keep thinking back to the last one of these I worked on, which was the Tokyo High Power 2.3 or whatever it was. It had bleeder circuits in its filter bank, so. Anywho, lid's back on it. I can't wait to run this. I've got it plugged into the 110/30 amp lick'em stick'em down there below the workbench. And I bet you we're going to see a little bit around 800 watts. I bet you that power supply running out of schmoo coming off that outlet. There's a reason we're a little shallowed up, but I ain't turning that gate voltage up no more for nothing. You get too carried away with the gate voltage, you're going to end up with, well, lids that are radically departed the environment, you know what I'm saying? I'm not going to lie, I've spent almost 2 days on this one thing. Well, almost 2.5 at this point. To make big watts on the watt meter is silly. Oh, look, I can turn it up. For 30 seconds, it made X amount of kilowatts. Yay. But it won't run there. The max the meter is going to let you read on the amplifier is 1,000 watts. And it's going to kick in at about, what, 900 and something? As it'll trip in and say, nope, you're overdriving, over output. So the total amount of power consumption is what they're right in the numbers on the front. So, anywho, one more screw, and we're going to quickly kick it through all the bands and make sure it all works and make sure that we're within spectrum quality. Got to remember, these 4 transistors in here, if I was to take and monoband out those devices and not have to try and spread the power out across such a diverse amount of frequency, which is all the modes, by the way, there's 2,000 watts worth of peak power out of each one of those transistors. We found that we can monoband out those parts and get them to do, with relatively low drive, roughly 1,000 watts for every 2 transistors. But because we're going to operate this thing between 160 and 6 meters. Following where I'm going? Oh yeah. Now we got airflow. Sounds right, looks right. Yay. All right. So first, for documentation's sake, we're on 80. We're over here on 80. At 012. Let's bring the amplifier online. That was me showing you input power at 012. So it looks like on the spectrum analyzer at 012. At 012, there's our 800 watts, no problem. At 0. And this is what it looks like coming out the back end of the pipe. Now, right now, I can tell you, based off of my previous statement, oh, it can get 2,000 watts. There's some ham guy out there right now that's going, no, but you can't do that cleanly because that'd just be a splatter box. Well, I strongly disagree. Like I emphatically disagree. We try to keep the max saturation of the signal coming out of the amplifier only occupying maybe 5 kcs, 6 kcs. That's a conversation for another day. All right, 40. Let's go back over here. At 012. All right, step on the foot pedal. At 012. There's 900 watts on 40. Just going up to 10 megahertz. So jump that up to 10. Radio's at 10. At 0. Okay. At 0. Let's come down over here. Let's look at it on 10 megahertz. At 012. There's our 900 watts of power. At 012. Nice and clean on the output side. Let's go to 20. 14 megahertz. Radio's changed. At 012. There's our 900 to almost 1,000 watts with at audio. At audio. About 100 watts going in. So at 01212. Nice and clean. I would really not put more than about 60, maybe 50 to 60 watts max in this thing if it was me. If it was me. Let's see, we'll start out at 18. They've got this labeled as 18 through 21, so we'll start out at 18 megahertz. Hello, audio. Hello, audio. Hello, 1212. Of course, the input on this. Hello, 1212. The reason I'm not making a big deal about the input is because of that big bank of input attenuators that run down this whole length of the heatsink. If you got a high-end input SWR, there's something wrong with your coax or a coax connector, or you're stupid and you've got it on a different switch. Don't be dumb with that switch either. That'll blow your whole shit up. So it'll blow everything up. Let's see. Let's go to 21 megahertz just to prove a point. 21 megahertz. Once again, hello, 1212. Oh wow, that's way down on power for that band. Imagine that. Hello, 12. Hello, 12. Double check. Yeah, we're on antenna A. Okay. Making sure. Hello, 12. There's our 900 watts once again. Hello, 1212. Now, the amount of time that I'm operating this thing is also making me build confidence in it. .24. Okay, so now we're at 24 megahertz. Hello, 1212. Hello, 12. There's our 800 watts. Now we're coming on the other end of the power band of the radio. Please note, I said 24 megahertz. It's 24 and 28. Let's go do 10 meters real quick and have some fun with this. Hello, 12. Hello, 1212. There's our 800 there. And let's go to 6. Take me to 50, babies. 50, babies. Hello, 1, 2, 1, 2. Hello, 1, 2. Hello. Now, who knows what I'm actually doing for power? Because guess what? My elements quit at 30, but the amp is definitely doing its job. Hello, 1, 2, 1, 2. Here's the radio. Hello, 1, 2, 1, 2. Here's the amplifier. Hello, 1, 2, 1, 2. We're making more power than we're putting in it. So this is our volts. Hello, 1, 2. Hello, 1, 2. Power supply amps. Power going forward. Hello, 1, 2. And of course, hello, 1, 2. Power coming back in reverse. Let's come on down here to 14 megahertz. Hello, 1, 2, 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Hello, 1, 2, 1, 2, 1, 2. Now we can tell that we are getting right on the borderline of making this trip. Let me show you what I mean. Look, look, look. Volts is the bottom scale. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. We're causing this light to blink. We are right there. This thing is producing the most power it can possibly put out. And so I'm trying to tell you is that we should probably reach up here, turn this down. Let's go over to our watt meter again. Hello, 1, 2. Hello, here's full chooch. Hello. We'll turn our amp down to about 50 watts, 60 watts of input power. Or the radio down to 50, 60 watts. Hello, 1, 2, 1, 2, 1, 2, 1, 2. And let's look at this. Hello, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 1, 1. We're right within the bottom end of the safety band. So 60 watts going in. Hello, 1, 2, 1, 2, 1, 2. 500, 600 watts here. Hello, 1, 2, 600 watts there. It's a 10-to-1 ratio, guys. All right, well, that's my customer right there actually calling me. And I'm gonna let him wait because I'm at the very tail end of this thing and I'm ready to be done. All right, my man, 4 new transistors completely overhauled, blah, 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 blah. Power supply for fan repair, la, 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 la. Brother, we pulled a miracle out of our ass by being able to find those transistors for you. I hope you're happy. I mean, I really hope you're happy. Guys, don't come calling to me to want to get these parts. I might be able to hit the transistor tree one more time, but after that, I mean, he's got only maybe 100 or 150 of these parts, and he really likes to bogart parts, but I do appreciate him coming up off these transistors just for me. And like I said, they're $120, $130 a piece for the legit, you know, made in Malaysia components. So I'm done, gentlemen. Thanks to Siglent, XS, McMahon, Bird, Coaxial Dynamics. Always, thank God for my Patreons. They're going to see this 24 or 48 hours before everybody else on the Interboob. And they're going to get a behind the scenes video tomorrow, Friday, and this weekend, because I got a huge project coming up. So on that note, gentlemen, I want to say thanks. I appreciate every single one of you. Peace. I'm out. I'll see ya. Bye.